All right, this is the last problem. It's the last section, it's the last chapter, it's the last thing that we're talking about in graph theory. It's called the traveling salesman problem, and it's different from the Chinese postman problem because the Chinese postman problem dealt with traveling along every edge at least once to deliver the mail. Well, a traveling salesman needs to go to different cities to sell things, so it's a much broader scale. So we're going to look at the vertices as being those cities that he's got to travel to. He's got to travel to every vertex at least once, and then he's got to get back home. So that's basically the problem. You're traveling to every vertex instead of along every edge. All right, so how do we find the cycle of least weight that visits every vertex exactly once? Remember, you don't want to revisit cities. So here's how we're going to do that. I need to find the least weight Hamiltonian cycle of a weighted complete graph. So the graph is complete. That's different from what we had before. So I can get from any vertex to any other vertex using exactly one edge. Different kind of problem than the Chinese postman problem. So there's no guaranteed strategy to solve this. This is one of those problems that has no guaranteed solution. You could, for very, very small problems, obviously figure out what the smallest weight subgraph would be, but once you get into problems where there are 20 and 40 and 50 vertices, there's not an algorithm that works every single time. So the best we can do is come up with an upper and lower bound. Okay, so we can say that I know that the best path is going to be at most this much, and I know that the best path is going to be at least this much. That's the best we can do. So I'm going to show you how to find each of those, and I'm going to go through an example with the exact same complete graph. So to find the upper bound, so this is either going to be equal to or it's going to be higher than the best possible solution. All right, so we're going to choose any starting vertex, consider all of the edges that start at that vertex and end at a different vertex, one that you haven't chosen yet, and from these you're going to pick the one with the lowest weight. Okay, and then you keep repeating until all vertices have been chosen, and then you complete the cycle by joining the last vertex with the first. So that's going to be an upper bound. Okay, it will definitely be a cycle. It may not be the best one though. So I start at any vertex. So let me start at A. Okay, and from A, I'm going to choose the smallest path from A to anything that's not A. So I've got a choice of 11 or 7 or 8 or 6. Well, it looks like 6 is my best choice. All right, and now from E, I obviously can't go back to A, so I've got to choose the edges that I haven't used yet that start at E and go somewhere else. So I can either go to 8 or 11 or 7, so my choice is going to be 7. Okay. Now from D, I can't go back to A, obviously, but I can go to B and I can go to C. B will cost me 8, C will cost me 10, so I'm going to go to B. And now the only other option I have is to go to C. It's the only vertex that hasn't been chosen yet, and then I go home. So if I add up all of those edges, I get a nice upper bound for what the best solution will be. Okay. Now to find the lower bound, I'm going to use what's called, the lower bound algorithm. All right, so what I'm going to do is I'm going to delete any vertex along with all of the edges that are adjacent to it. Then I'm going to find the minimum spanning tree using any algorithm, either Prim's or Kruskal's, to find the minimum spanning tree. And then I'm going to add the weight of the minimum spanning tree to the length of the two shortest deleted edges. Okay, and this is a lower bound because it doesn't necessarily make a cycle. Okay, so using the same graph as before, I have randomly decided that I'm going to delete vertex A, so let me just toss it over here, but let me also keep in mind that the shortest two edges that I deleted were 6 and 7, so that's 13, so let me just make a note here that I will be adding 13 to the minimum spanning tree that I get from here. So I'm going to use Kruskal's algorithm, that's the one I like, to find the minimum spanning tree of these 4 vertices. So finding the shortest edge, that's a 7. Finding the next one, it's either this 8 or this 8. So I'm going to randomly choose this 8. I cannot now choose this 8 because that would make a cycle. So I move on and I choose this 10. I've got 3 edges now, which is 1 less than the number of vertices that I have, so I am done. So if I add these edges together, I've got a 7, an 8, and a 10, so that is a total of 25. And so the lower bound for this problem would be 38. Okay, so I know that the best solution is going to be 38 or more. All right, and that's how you solve traveling salesman problems. If you have any questions, please let me know, and I will see you tomorrow.